Okay, so let's talk about these boxes and items, otherwise known as the occupancy problems. I want to start with the chart. So I got the top of this. There we go. That should be visible. Um, so notice there's three things that we can decide. And this tool isn't going to work for all types of problems, so it's important to be able to recognize when this tool works, and we'll go through some examples of how to use it. So we really have three possible choices with putting items into boxes. And I like to draw this out, like so you can think of literal boxes, and a lot of times the problems we may have to kind of bend our definition of what a box or what an item is. But let's say you had 10 items, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 items, and you're going to put them in four boxes. And let's kind of move our way around the chart. So let's start with the way they're drawn now. They kind of look indistinguishable. So there's nothing like putting this ball in a box is the same as putting this ball in a box. There's no way to tell them apart. So this would be indistinguishable items. So first of all, and the boxes right now look indistinguishable too. So if you put two balls in the one on the left and one in the second one, that would be the same as one here in this box and two here. At this point, there's nothing distinguishing the boxes. So we would be right here. And so then the only question would be, we have these 10 items. So n equals 10, boxes equals 4. And if if we're saying how many ways to get these 10 balls into these four boxes, and you have to make sure there's at least one ball in a box, well, that's going to be this right here. So the answer would be P 10 4. Why? Because the balls are all the same, identical. The boxes are all the same, nothing differentiating them. And we said there has to be at least one in each box. Each box must be non-empty. So this is how many ways. To know what this number is, we'll talk about that separately. But just knowing this is the answer is what I want to focus on now. Or everything the same here, except we're going to allow empty boxes. So it might be that there's 6 in one box, 4 in another, and 2 empties, for example. And that would be the same as 4 empty, 6 empty, right? Because these boxes are identical. There's nothing telling them apart. If that's the case, we're then looking at this as our answer. So that would be P, n plus k is 14, and then k is 4. Now, so that takes care of these two situations. Let's say that these boxes were distinguishable. So maybe there's a red box and a green box and a blue box and a yellow box. So now we're asking something like, okay, we have these 10 indistinguishable items. So we're still over here. But now they're being put into distinguishable boxes. What I mean by that is if we put 2 in yellow and 3 in red, that's different than putting 3 in yellow and 2 in red. Those are two different things because the boxes are now distinguishable. So we've now moved up to this quadrant of our graph. And again, we just ask now, are we making sure there's at least one in each of the boxes? If so, then we're in situation A. So we would have C, which is combinations, by the way. N minus 1 is 9. K minus 1 would be 3. Okay. Or are we saying, no, it's okay. You could have 5 in yellow, 5 in red, and none in green and blue, for example. If that's the case, then we'd be in situation B, where we're allowing empty boxes. And that would be C, n plus k minus 1. 10 plus 4 minus 1 would give us 13. and k minus 1 would be 4 minus 1. So the answer would be there's 13 choose 3 or 13 combination 3 ways to put 10 identical balls into 4 boxes that are different, 4 differently colored boxes, if if we're okay with there being empty boxes in there. So that takes care of this side. Those are all the indistinguishable items. Now, let's say that these balls are distinguishable. So how am I going to do that? Well, let's think of them as like pool balls. Maybe they each have a number on them. I'm not going to even attempt to draw the number actually on the ball, but let's say that that number was written on the ball. So, for example, if you have balls 1 and 3 in yellow, that's different than having balls 4 and 6 in yellow, even though there's still two of the balls, because now the balls are, these items are now distinguishable. So now we're over on this left half of the chart. And right now, let's keep with our colored boxes. So we're still up here in distinguishable boxes. And it's a matter of each box must be non-empty. So if we're saying these 10 numbered balls, and these could be people, these could be 10 different types of candy, these could be whatever 10 different items that are distinguishable. You can tell the difference between them, and they count differently in the solution. If that's the case, and we need to make sure that we get at least one of the items in each bag here, then we're up in this situation. So we'd have 4 factorial, k equals 4. Sterling number, again, we'll talk about those in a separate time. N is still 10, k is still 4. So that would be right there. 10 distinguishable items, distinguishable boxes, making sure that none are empty. If you're okay with empties, if you're putting 10 items into these 10 different items into these 4 distinguishable boxes, and you're okay with empty boxes, then it becomes k to the n, which would be 4 to the 10th power here. That takes care of those two. And then finally, indistinguishable boxes. So we're going to leave our items numbered, and we're going to return to the case where all of these boxes are exactly the same. Ignore the color peeking behind the black here. We're going to just pretend these are all exactly the same. In other words, they're indistinguishable. But this time the balls here, they do have these numbers on them. So we're still distinguishable items, indistinguishable boxes. This is where we'd get, if we're not okay with empties, so each of these 4 has, maybe we do 4, 3, 2, 1, for example, which would be the same as 1, 2, 3, 4, because the boxes, there's nothing telling them apart. We're just saying one box has 1, one has 2, one has 3, one has 4. How many ways? Well, it's this sterling number 10, 4. And then finally, maybe the messiest way, but if we were allowing empties, so maybe we have all 10 in one box, or maybe we have 5 and then 3 and then 2, well then that's going to be, you can just keep the format here. I equals 1 to 4 of S 10 I. And if you wanted to write this out, this is S 10 1 plus S 10 2 plus S 10 3 plus S 10 4. In other words, the sum is just saying we start where I is 1, we plug in 1 for I, and we keep raising I by 1 until we hit the maximum of 4 right here. All right, so those are how the different boxes and items and empty, non-empty work. Let me go ahead and put a separate video for applying these.